Produced with the cooperation of the United States Air Force. Man's early attempts to build an aircraft that could take off straight up produced some very strange-looking birds. Most of them never even got off the ground. But over the years, the designs and performance improved. Today, there are all kinds of aircraft that can take off and land vertically. Simple, lightweight machines, they are easy to operate, and the passenger is his own pilot. Primarily designed to move an infantry soldier faster than most other forms of transportation, they're being tested for that purpose, and for the present will be limited to that use. They appeal to man's deep desire to move through the air, with the ability to stop and start whenever and wherever he pleases. The roaring engines that announced the arrival of the jet age also amplified some of the old problems of aircraft operations, especially for military planes. Longer, heavier, thicker runways are needed for takeoffs and landings, and these require more time and effort to build. A longer takeoff also means slower response to an attack warning. As the speed of jets increases, so do their handicaps under certain combat conditions. Many attempts were made by the military to get around the problem of runways. The Zero launch used a rocket to thrust a plane into flight, but it needed a ground crew and complex controls to launch it. It still required a runway for landing. Aviation engineers knew the problem could not be bypassed. As they tried to solve it, one thing became clear to them. This was not so much a new problem as an old challenge in a new situation. Required a jet-age aircraft that could take off and land vertically. Soon, test models were being designed and built, studied and modified to explore the possibilities. In one experiment, a jet engine on a leash forced itself upward with its own powerful thrust. A system of remote controls was developed to maneuver the tethered engine upwards and down and from side to side. The Bell XV-3 was an attempt to combine the two basic flight systems of the pre-jet age, a conventional plane body with helicopter rotors mounted on the wingtips to lift it and land it vertically. More ingenious was the Convair FXY-1. It stood on its tail for the takeoff and got its lift from a double set of propellers geared to rotate in opposing directions. With these contra-rotating propellers, it literally screwed itself up into the air. Then it leveled off into horizontal flight. Hiller X-18 test model is based on the same principle as the Convair, but the X-18 has wings that tilt to a forward position and change its flight direction. Engineers knew that all these experiments were only preliminary studies. The next step was to apply these findings to aircraft powered by jets. The Bell VTOL did exactly that, in spite of its primitive appearance. Its jet engines were mounted on swivels to change the direction of their thrust. It was put together with scrounged and salvaged parts: a Schweitzer glider body, Cessna wing, the throttle of an outboard motor. But it proved that the qualities of jets and helicopters could be combined. The Bell X-14 carried this idea a step further. It uses the deflected slipstream of its jet thrust to lift itself off the ground, straight up. One of the strangest looking deflected slipstream models is this new Ryan development, powered by a turboprop engine geared to 2 propellers. It's equipped with huge flaps which change the direct of propeller thrust from horizontal to vertical and so lift the airplane. Several years earlier, Ryan engineers had another experimental model under wraps in an isolated section of the San Diego plant. On November 23rd, 1953, they prepared for a crucial test. The same team had already worked 6 years. William Immenshoe, seldom without a pipe, chief of test operations. Charlie Ackerman, the project engineer. And for this very special project, a very special test pilot, Peter Gerard, chief aerodynamics engineer, until this new challenge came along. The challenge: design and build a vertical takeoff and landing aircraft powered by a single jet engine. First sponsored by the Navy, then taken over by the Air Force, this test model was developed from the tethered engine, operated by remote controls. Now Peter Gerard was going to see whether it could be controlled by man. The others would check every detail of its performance on a duplicate instrument panel. Pete Gerard was risking his life to prove that the concept of hovering jet flight would work. Even though they knew that it should work, hoped that it would, they could hardly believe their own eyes. The world's first piloted hovering jet flight was over. The concept was right, and the tethered engine could be controlled by man. For all of them, the triumph of this moment had more meaning for the future than the past. Now they could proceed with plans to build the actual aircraft. First came the long, exacting process of designing the plane, determining every detail of its structure in advance. Then construction began. The tethered beast, as the first test model was affectionately known, was evolving into one of the world's most advanced aircraft, the Ryan X-13 Vertijet. As each part was fabricated, every conceivable factory check for safety and function was made. Then one day, late in 1955, the X-13 left the Ryan plant, wrapped in secrecy and covered with the high hopes of its builders. It was trucked along Highway 395 to the desert silences of Edwards Air Force Base, the Air Force Flight Test Center for Experimental Aircraft. Here, before it could take to the air, additional structural changes had to be made. For test purposes, a temporary landing gear was added, a pogo rig. For this aircraft that stood on its tail for the takeoff, the pogo rig gave it support and protection. On May 28, 1956, Pete Girard mounted to the cockpit, but this time he was getting into a real airplane, and there was no tether to restrain the beast. The beast was as gentle as a lamb during its first free, hovering jet flight. After months of work in the blazing heat of the desert, testing and retesting, discussing and testing again, one by one, the technical bugs were ironed out. Now, the time had come to prepare for the next step. A hook, a real one, not this one, would eventually replace the pogo rig for landings. But first, Pete Girard had to practice slipping the hook over the cable on which the Vertijet would land. His skill makes these simulated hook-ons look deceptively easy, but there's no deception in the exacting controls, which permit a pilot to handle the 10,000-pound thrust of the engine with the precision of a fine instrument and enable the aircraft to perform with the easy grace of a ballerina. "4:30 a.m., April 11th, 1957. Engineers and technicians arrive at the Ryan test hangar. Today, a momentous question must be faced and answered. It's a question these men have asked themselves over and over during these past 10 years, but now it comes from Air Force headquarters in the Pentagon. Is the Vertijet ready for its first full transitional flight? mechanics, designers, and engineers all know the reasons for every past mechanical failure or delay. And now they're anxious to begin the final tests. In another part of the hangar, the X-13 gets a final inspection. Every detail is checked again and again. The briefing is long and involved because the test flight will be complicated. To complete its mission, the X-13 will have to make 4 flights in one. A vertical takeoff, transition from vertical hovering to horizontal flight, another transition back to the vertical, and a vertical hook-on landing. The trailer bed is towed into position and anchored to the ground. Pete Girard makes his own personal last-minute checkup. Today, nothing can go wrong. At 6:55 a.m., Girard climbs into the cockpit. The preliminaries are over. All that remains is the big question. Will the Vertijet do what no other aircraft has ever done before? Will it fulfill the belief of all the men who have worked so long for this day? From this crow's nest, another pilot will guide Girard by hand signals during the moments before the hook leaves the cable. Vertical position for vertical takeoff from a cable that serves as a landing field, a cable held by the stout supports of the now vertical trailer bed. As though sensing its own power, the Vertijet strains to pull free. Girard isn't ready yet. He tests his controls. Now he's ready to go. Mission number 1, vertical takeoff, completed. Mission number 2, transition to horizontal flight, completed. And in horizontal flight, it has the speed and performance of a jet interceptor. Mission number 3, transition from horizontal flight to vertical hovering, completed. From the crow's nest, Gerard receives signals as he hovers and approaches the trailer. Mission number 4, vertical hook-on landing, completed. The world's first vertical takeoff and landing jet flight mission is completed. For these men, the successful culmination of 10 years of effort and proof that the theory was sound. A few months after its historic first flight, the X-13 Vertijet comes to Washington to show the men in the Navy and Air Force who had supported its development that it really does not need an airfield. Man's attempts to build aircraft that can take off straight up and land straight down are still producing strange-looking birds. But these birds get off the ground and fly. Powered by jet engines and freed from the need for runways and airfields, they prove that the promise of the air age is as limitless as the skies.